Right now, inside your body, trillions of invisible prisons are holding reality together. If just one of them failed for a single instant, you would detonate with more force than every nuclear weapon on Earth combined. This is the strong nuclear force, and it's the most powerful thing you've never thought about. Scientists measure its strength as 100 times greater than electromagnetism, in a number so large it breaks calculators. 100 trillion times stronger than gravity. If gravity were a whisper across a football field, the strong force would be a scream that shatters concrete. Is it raw strength, range of influence, the ability to create or destroy? By the end of this investigation, you'll discover that the answer is far stranger than any science fiction. Let's start where all matter begins, inside the atom. Every proton in your body contains 3 quarks, bound together by particles called gluons. These quarks should explode apart instantly. They're positively charged, and positive charges repel each other with tremendous force, like trying to push 2 powerful magnets together. Yet somehow they remain locked in place. It's like trying to cut a chain, only to watch it grow new links faster than you can cut. This force operates at distances so small that a femtometer, 1/4,000,000th of a meter, seems vast. At these scales, the familiar world of everyday physics breaks down completely. Space and time themselves become uncertain, fluctuating according to the strange rules of quantum mechanics. Without the strong force, you wouldn't exist. Protons would fly apart due to electromagnetic repulsion. Atomic nuclei couldn't form. The fusion reactions that power every star in the universe would never ignite. Reality would contain nothing but hydrogen atoms and free electrons drifting through eternal darkness. Yet despite its absolute dominance at the subatomic scale, the strong force has a fatal weakness. Step back just slightly to the scale of molecules, cells, or human bodies, and it becomes completely irrelevant. Other powers take control. This is the first hint that cosmic power isn't about strength alone. It's about reach. It's about duration. It's about the ability to shape reality across different scales of existence. But the strong force is just the beginning. Out in the depths of space, explosions are occurring that make this subatomic powerhouse look gentle by comparison. These cosmic detonations release more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. And that's where our journey takes us next. Gamma ray bursts. Somewhere in the cosmos right now, a beam of pure energy is tearing through space at 99.99% the speed of light. For just 10 seconds, it will release more power than our sun will produce in its entire 10 billion year lifetime. This is a gamma ray burst, and it represents the brightest explosion the universe can create. These cosmic titans occur when the most massive stars in existence, giants containing 20 to 100 times the mass of our sun, finally exhaust their nuclear fuel. When fusion stops, gravity wins the ultimate battle. The star's core implodes in less than a second, collapsing from the size of Earth to just 12 miles across. But the collapse doesn't end there. The core continues shrinking until it punches a hole through space-time itself, creating a newborn black hole. Around this black hole, a disk of superheated material spins at significant fractions of light speed. Magnetic fields, twisted and amplified by the collapse, act like cosmic cannons. These fields launch jets of matter and energy from the black hole's poles at 99.9% the speed of light. The jets punch through the dying star like bullets through tissue paper, emerging as focused beams of destruction. Think of a laser beam that maintains its focus while traveling from Earth to the nearest star. These jets accomplish something similar on scales millions of times larger. The collimation is so perfect that astronomers can detect them from billions of light years away as thin, straight lines drawn across the cosmos. A single gamma ray burst can outshine 1,000,000,000,000 stars. If you could see gamma rays with your eyes, these explosions would appear brighter than the full moon, even from galaxies billions of light years distant. To put that in perspective, imagine standing on Earth and watching a flashlight beam from Alpha Centauri, 4 light years away, appear as bright as a car headlight shining in your face. That gives you a sense of how impossibly powerful these events are. But here's what makes gamma ray bursts truly terrifying. They're directional. The jets are narrow, perhaps just a few degrees wide. This means we only detect gamma-ray bursts when they happen to point directly at Earth. For every burst we observe, hundreds more are firing in other directions, invisible to our instruments. If a gamma-ray burst occurred within our galaxy and pointed at Earth, the consequences would be catastrophic. The radiation would strip away the ozone layer in seconds, exposing the surface to lethal doses of ultraviolet light. Some scientists believe a gamma-ray burst may have caused one of Earth's ancient mass extinctions. Fortunately, the nearest star capable of producing a gamma-ray burst is thousands of light years away and isn't aimed in our direction. We can observe these cosmic catastrophes from a safe distance, watching the universe demonstrate power that makes nuclear weapons look like firecrackers. The light we detect from gamma-ray bursts carries news of stellar deaths from when the universe was young. Scientists have detected bursts so distant their light began traveling less than 1 billion years after the Big Bang, when the first generation of massive stars lived fast and died violently. These ancient beacons seeded space with heavy elements essential for later generations of stars and planets. Every atom heavier than helium in your body was forged in stellar explosions. The oxygen you breathe, the carbon in your DNA, all of it came from dying stars. But gamma-ray bursts, despite their incredible power, operate on timescales. Of seconds to minutes, they're brief flashes of cosmic violence. What if power isn't about intensity alone, but about duration? What if the most powerful forces are those that operate continuously, reshaping reality over billions of years? In the darkness between galaxies, something is doing exactly that. Dark energy. Across 13.8 billion light-years of space, an invisible force is winning a cosmic war. Every second, it pushes galaxies farther apart, stretching the very fabric of space-time itself. This mysterious power makes up 70% of everything that exists, yet we know almost nothing about what it actually is. Dark energy is not like other forces. It doesn't weaken with distance like gravity or electromagnetism. Instead, as space expands, more dark energy appears to fill the void. The bigger the universe becomes, the faster it expands. It's like a cosmic gas pedal that only knows how to accelerate. Scientists discovered this force by accident in the 1990s while studying distant supernovae. They expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. Instead, they found the opposite. Space is expanding faster today than it was billions of years ago. The discovery was so shocking that the astronomers checked their calculations dozens of times, convinced they'd made an error. They hadn't. The universe really is accelerating, as if some invisible hand is pulling everything apart with increasing strength. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath, causing every point on the balloon surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean, powerless to resist. The tide? Here's where it gets truly strange. The amount of dark energy in the universe increases as space expands, but it turns out he may have been right for the wrong reasons. Other theories propose that dark energy could be a dynamic field that changes over time, or even evidence that our understanding of gravity needs major revision on cosmic scales. Some physicists suggest we might be observing the influence of extra dimensions beyond the 3 spatial dimensions we experience. The consequences of dark energy are profound. In the far future, it will tear apart everything we see. First, galaxy clusters will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness. But here's the paradox. If dark energy is the most powerful force in the universe, the only force strong enough to overpower gravity on cosmic scales, why? Does it feel so weak in our everyday lives? Why don't you feel yourself being stretched apart right now? The answer reveals something fundamental about power. Dark energy only matters at the largest scales, across billions of light years. At smaller scales, galaxies, solar systems, planets, human bodies, it's completely negligible. Other forces dominate. This is the mirror opposite of the strong nuclear force. The strong force is incredibly powerful, but only at tiny distances. Dark energy is incredibly powerful, but only at vast distances. Neither can claim absolute dominance across all scales of reality. So if we're searching for the most powerful thing in the universe, we need to keep looking. We need to find something that combines extreme power with the ability to shape reality across multiple scales. And in the collapsed cores of dead stars, we find exactly that. Neutron, stars, and magnetars. Imagine taking a mountain and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack the mass of our sun into a sphere just 12 miles wide. Their surfaces are made of atomic nuclei crushed together so tightly that a single teaspoon would weigh 6 billion tons on Earth. The gravitational field is so intense it warps light itself, bending photons around the star in impossible trajectories. But gravity isn't their most terrifying feature. Neutron stars possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, creating beams of radiation that sweep across space like cosmic searchlights. The magnetic field of a typical neutron star is so powerful it could erase every credit card on Earth from a distance of 600 miles. If you could somehow approach within 1,000 kilometers, the magnetic force would be strong enough to distort the atoms in your body. The iron in your blood would align with the field lines. You would literally feel yourself being pulled apart at the molecular level. When these magnetized neutron stars spin, they become pulsars, firing beams of radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, faster than a kitchen blender, yet maintain perfect timing that rivals the most accurate timepieces ever built. Each pulse marks another rotation of a stellar corpse spinning in the darkness. The surface of a neutron star is a realm where familiar physics breaks down. The magnetic field is so strong it stretches atoms into needle-like shapes aligned with the field lines. Normal atomic structure cannot exist. Instead, exotic forms of matter appear that exist nowhere else in the universe. Any ordinary matter that falls onto a neutron star's surface would be compressed instantly into a layer just millimeters thick. The gravity is so intense that a marshmallow dropped from waist height would hit the surface with the force of a hydrogen bomb, releasing more energy than all the explosives used in World War II. But some neutron stars take magnetic power even further. Magnetars have magnetic fields 1,000 times stronger still, approaching the maximum strength allowed by the laws of physics. When these objects experience magnetic quakes, their crusts crack and shift like tectonic plates on Earth. But instead of earthquakes, magnetars produce magnetic cataclysms that release more energy in 1/10 of a second than our sun produces in 100,000 years. These magnetic flares create giant bursts of gamma rays and X-rays that can be detected from across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light-years, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense it affects the vacuum of space itself. Quantum mechanics predicts that at extreme field strengths, empty space should become birefringent, like a crystal that splits light into different polarizations. Astronomers have detected this effect around magnetars, confirming field strengths that exceed anything achievable in terrestrial laboratories by factors of billions. But here's the question that connects back to our search for ultimate power. Magnetars are incredibly powerful, but they're also incredibly rare. Only about 30 have been identified in our entire galaxy, and their extreme magnetic fields decay over time, typically lasting just 10,000 years before fading to normal neutron star levels. So is a magnetar more powerful than dark energy, which operates continuously across the entire universe? Is it more powerful than a gamma ray burst, which releases more total energy but over a shorter time? These questions force us to refine our definition of power. We're not just looking for raw strength or energy output. We're looking for the ability to fundamentally alter reality, to create, to destroy, to reshape the cosmos in lasting ways. And for that, we need to look at objects that combine extreme density with extreme gravity in ways that literally tear holes in space-time. Black holes. At the heart of our galaxy sits a monster 4 million times more massive than the Sun. Sagittarius A devours everything that ventures too close. Gas clouds, rogue planets, entire star systems. Yet this giant is considered small compared to the true titans lurking in distant galaxies. Some supermassive black holes contain the mass of 40 billion suns compressed into a region smaller than our solar system. They are cosmic vacuum cleaners with gravity so intense that nothing, not even light, can escape once it crosses their event horizon. Space and time bend around them like water swirling down a drain. Near the event horizon, time slows to a crawl compared to the outside universe. If you could watch someone fall into a black hole from a safe distance, you would see them slow down, redden, and eventually freeze at the edge, their image preserved forever while they experience something entirely different, a swift passage into oblivion. These gravitational monsters didn't grow slowly. The most distant quasars shine from when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in cosmic infancy. Normal stellar evolution simply cannot explain their existence. The leading theory suggests these giants began as massive seeds formed directly from collapsing gas clouds in the early universe. Unlike stellar mass black holes that form from dying stars, these primordial monsters may have contained hundreds of thousands of solar masses from birth. This head start allowed them to grow rapidly by consuming surrounding matter and merging with other black holes. When gas spirals into a supermassive black hole, friction heats it to temperatures of millions of degrees. The material forms an accretion disk that glows brighter than 100 billion stars. The disk rotates so rapidly that matter near the inner edge travels at significant fractions of light speed, experiencing time dilation that would stretch seconds into hours for outside observers. The most luminous quasars powered by feeding black holes can be seen across the observable universe, cosmic lighthouses broadcasting their presence across billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem dim by comparison. But the truly remarkable power of black holes isn't just their ability to consume matter, it's their ability to launch it back into space. The most violent black holes launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and preventing new stars from forming across vast regions of space. How does an object defined by its ability to trap everything manage to launch the most powerful jets in the universe? The answer lies in the accretion disk. Magnetic fields threading through the disk become twisted by the extreme rotation, storing enormous amounts of energy. When these field lines snap and reconnect, they act like cosmic catapults, flinging material outward at relativistic speeds. Recent observations have revealed black holes that seem too massive for their host galaxies, breaking the normal relationships between central black hole mass and galactic properties. These overmassive giants challenge our understanding of how galaxies and their central black holes evolve together. But even supermassive black holes have limits. They can only grow so fast before their own radiation prevents more matter from falling in. When a black hole feeds too rapidly, the energy released by infalling matter creates outward pressure that pushes away additional fuel. This creates a natural limit called the Eddington limit. So black holes, despite their reputation as the ultimate cosmic predators, are constrained by the very process that makes them luminous. They can't simply devour the universe without limit. This brings us back to our central question. Black holes are immensely powerful. They bend space-time, trap light, launch galaxy-scale jets. But are they the most powerful thing in the universe? Or is there something even more fundamental, something that operates on scales that make even supermassive black holes seem small? Quasar jets. 4 billion light-years from Earth, a black hole the size of our solar system is launching a beam of particles that stretches across an entire galaxy. This jet of superheated plasma moves at 99.9% the speed of light, carrying enough energy to power 1 trillion stars while maintaining perfect focus across distances that dwarf human comprehension. Quasar jets are born in the chaos surrounding supermassive black holes, where space-time itself becomes a battlefield between gravity and magnetism. As matter spirals inward toward certain doom, it forms an accretion disk, spinning at incredible velocities. The disk becomes a cosmic dynamo, generating magnetic fields of extraordinary strength. These magnetic field lines act like cosmic particle accelerators, channeling material from the inner regions of the accretion disk into narrow beams that shoot outward from the black hole's poles. The same gravitational forces that should drag everything into oblivion instead launch some material back into space at relativistic speeds. The jets are so straight they appear drawn with a cosmic ruler. They maintain their narrow focus across distances of hundreds of thousands of light years, threading through space with precision no human technology could match. When astronomers observe these jets with radio telescopes, they appear as thin lines even when viewed from billions of light years away. The particles within these jets carry energies millions of times greater than anything we can create in our most powerful particle accelerators. Individual protons race along the jet at speeds so close to light that their relativistic mass increases by factors of thousands, turning ordinary matter into cosmic bullets of incredible power. When a quasar jet points directly at Earth, we see it as a blazar. The light appears to brighten and fade as the beam sweeps past us like a lighthouse. These blazars can vary in brightness by factors of hundreds within days or hours, as turbulence in the jet creates bright knots of emission, traveling toward us. Sometimes these knots appear to move faster than light across the sky. This isn't actually possible. It's an illusion created by geometry. When material moving at 99% light speed travels almost directly toward us, it appears to cover vast distances in impossibly short times because the light from different positions arrives at nearly the same moment. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, blowing bubbles in the surrounding gas that persist for hundreds of millions of years. These cosmic blowtorches can prevent new stars from forming across regions spanning millions of light years, effectively sterilizing vast volumes of space. In the Perseus galaxy cluster, astronomers discovered cavities in the hot gas carved by jets from the central black hole. These bubbles are so large they could fit dozens of Milky Way galaxies inside them. The energy required to create these structures exceeds the combined output of all the stars in the cluster. Recent observations have revealed jets that extend far beyond their host galaxies, stretching into the intergalactic medium where they continue to propagate for millions of years. These ancient jets carry the signature of black hole activity from cosmic epochs when the universe was younger and more violent than today. But here's the crucial insight about quasar jets. They represent the ultimate conversion of gravitational potential energy into kinetic energy. Matter falling toward a black hole releases more energy per unit mass than any other process in the universe, including nuclear fusion. When hydrogen fuses into helium in a star's core, it converts about 0.7% of its mass into energy. When matter falls into a black hole and powers a jet, it can convert up to 40% of its mass into energy through the extraction of the black hole's rotational energy. This makes black hole jets the most efficient energy conversion process known to physics. They take the pull of gravity, the weakest of the fundamental forces, and amplify it through rotation and magnetic fields into beams that can reshape galaxies. Yet even these galaxy-spanning jets have a finite reach. Eventually, they slow down, dissipate, and fade. Their power, while immense, is temporary. So we must ask again, what is power? Is it the ability to create spectacular destruction? Or is it something quieter, more persistent, a force that operates continuously across the entire cosmos? Neutron-star collisions. Two city-sized objects spiral toward each other through the darkness of space, locked in a gravitational death dance that has lasted for millions of years. They are neutron stars, the crushed cores of massive stars, and their collision will create the most violent event in the nearby universe, while forging elements more precious than anything in a king's treasury. Each neutron star contains more mass than our sun, compressed into a sphere just 12 miles across. As they orbit closer and closer, the neutron stars distort each other's shapes through pure gravitational force. Tidal forces stretch and squeeze these incredibly dense objects, generating heat that makes their surfaces glow with temperatures of millions of degrees. The orbital dance accelerates as energy bleeds away through gravitational waves. These waves are ripples in space-time itself, stretching and compressing the very fabric of reality as they race outward at light speed. Advanced detectors on Earth can measure these waves even though they change distances by less than 1/10,000th the width of a proton. In the final seconds before collision, the neutron stars complete hundreds of orbits per second, whirling around each other faster than a helicopter blade. The gravitational waves they generate become so powerful they carry away energy equivalent to 3 sun masses in just the last few seconds before impact. When the neutron stars finally touch, they create a brief flash of gamma rays followed by a longer-lived explosion called a kilonova. The collision literally shakes the universe, sending gravitational wave signals that can be detected from billions of light years away. On August 17, 2017, astronomers detected gravitational waves from a neutron star merger 130 million light-years away. Within seconds, gamma-ray observatories detected a burst from the same location. Within hours, telescopes around the world turned to observe the aftermath. For the first time in history, humanity witnessed a cosmic collision with both gravitational waves and light. The merger forges elements heavier than iron through a process called rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are bombarded with so many neutrons they can barely absorb them fast enough. This creates unstable neutron-rich isotopes that decay into stable, heavy elements. A single neutron star merger produces quantities of gold equivalent to several Earth masses, along with comparable amounts of platinum, uranium, and other precious metals. Every gold ring, every platinum necklace, every uranium atom in Earth's core, all of it came from neutron star collisions billions of years ago. The collision ejects this stellar treasure at speeds approaching 1/3 the speed of light, seeding nearby space with materials that will eventually find their way into future generations of planets and asteroids. The ejected material glows with radioactive decay for weeks, creating a kilonova that shines with the combined light of hundreds of millions of suns. But the collision does more than create heavy elements. It also provides crucial tests of physics under extreme conditions. The gravitational waves and light arrive at Earth at nearly the same time, confirming that gravity travels at the speed of light. The observations constrain the equation of state of neutron star matter, helping physicists understand how matter behaves at densities where atomic nuclei touch. Some neutron star collisions result in a hypermassive neutron star that survives for seconds or minutes before collapsing into a black hole. Others create a black hole immediately. The outcome depends on the total mass and the rotation rates of the merging objects. These collisions represent the culmination of billions of years of stellar evolution. 2 massive stars were born, lived for millions of years, exploded as supernovae, and left behind neutron stars that orbited each other for millions more years before finally merging. The entire history of the universe is written in these events. But here's what makes neutron star collisions particularly significant in our search for ultimate power. They don't just release energy, they create new matter. They forge the building blocks of planets and life. They don't just destroy, they create. Perhaps true power isn't about destruction at all. Perhaps it's about creation, transformation, and the ability to leave lasting marks on the universe. Supernovae. In a binary star system 30 million light-years away, a white dwarf star is slowly stealing material from its companion. For millions of years, hydrogen gas flows from the larger star onto the compact remnant, building up layer by layer. This stellar vampire is approaching a deadly threshold that will trigger one of the universe's most precise explosions. White dwarf stars are the dense cores left behind when sun-like stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants pack the mass of our sun into a sphere the size of Earth, creating matter so dense that a teaspoon would weigh as much as a car. The stolen material accumulates on the white dwarf's surface, compressed by gravity into a thin shell of hydrogen. The white dwarf acts like a cosmic pressure cooker, slowly heating the stolen matter until conditions become ripe for catastrophe. When the white dwarf reaches exactly 1.4 times the mass of our sun, something extraordinary happens. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that electron degeneracy pressure can support. Beyond this point, the star can no longer hold itself up against its own gravity. The accumulated material ignites in a runaway thermonuclear explosion that tears the entire star apart in seconds. The explosion propagates through the white dwarf like a flame front racing through cosmic dynamite, converting carbon and oxygen nuclei into iron and nickel through explosive nuclear fusion. This is a Type Ia supernova, and it represents one of the most precisely violent events in the universe. Every Type Ia supernova releases almost exactly the same amount of energy because they all involve the same massive material undergoing the same nuclear reaction. This cosmic standardization makes them perfect tools for measuring distances across billions of light years. Astronomers can observe a Type Ia supernova in a distant galaxy, measure its apparent brightness, and calculate its distance with remarkable accuracy. This technique led to the discovery of dark energy in the 1990s. The explosion shines with the light of 5 billion suns visible from galaxies billions of light years away. For weeks, a single exploding white dwarf can outshine an entire galaxy containing hundreds of billions of normal stars. The brightness peaks quickly and then fades over months as radioactive elements created in the explosion decay and release their energy. But Type Ia supernovae aren't the only kind. When massive stars, at least 8 times the mass of our Sun, exhaust their nuclear fuel, they explode as Type II supernovae. These explosions are different, powered not by thermonuclear detonation but by gravitational collapse. A massive star spends its life fighting gravity through nuclear fusion. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. Each fusion stage releases less energy and burns faster than the last. The final stage, silicon fusing into iron, lasts just a few days. Then the fusion stops. Iron cannot release energy through fusion. The star's core has become a dead weight, unable to support itself. In less than a second, the core collapses. Electrons are forced into protons, creating neutrons and releasing vast numbers of neutrinos. The collapse stops when the core reaches neutron star density. The infalling outer layers bounce off this suddenly rigid core, creating a shock wave that races outward through the star. Within hours, the shock wave reaches the surface and the star explodes. Type II supernovae E are less predictable than Type Ia events, but they're far more common. They're also the primary source of elements from oxygen to iron in the universe. The calcium in your bones, the iron in your blood, these atoms were forged in Type II supernovae billions of years ago. The explosion scatters these elements across vast regions of space at speeds of thousands of miles per second. The shockwave triggers new waves of star formation in nearby gas clouds while simultaneously enriching them with heavy elements necessary for planetary formation. Every supernova leaves behind either a neutron star or a black hole, depending on the mass of the original star's core. These remnants continue to influence their surroundings for millions of years, heating surrounding gas and creating expanding shells of debris that can be detected across the electromagnetic spectrum. But supernovae, despite their incredible power, are still just stellar explosions. They reshape local regions of galaxies, but they don't fundamentally alter the universe itself. To find that kind of transformative power, we need to look at events that occur on even larger scales. Galaxy cluster collisions. 2 massive galaxy clusters race toward each other at speeds of thousands of miles per second. Each cluster contains thousands of galaxies, trillions of stars, and vast oceans of superheated gas that glow with X-ray light. When these cosmic titans collide, they create the most energetic events in the universe since the Big Bang itself. Galaxy clusters are the largest gravitationally bound structures in the cosmos. The Coma cluster alone contains over 1,000 galaxies and has a total mass equivalent to 100 trillion suns. When clusters of this magnitude collide, the energy released exceeds the combined output of all the stars in both clusters by factors of millions. The collision begins slowly by cosmic standards, with the clusters approaching each other over hundreds of millions of years. Dark matter, which makes up most of each cluster's mass, feels only the pull of gravity and passes through the collision relatively unaffected, like 2 clouds of fog interpenetrating. But the hot gas that fills the space between galaxies experiences a very different fate. As the clusters merge, their gas clouds slam into each other at velocities approaching 5,000 miles per second. The collision creates shockwaves that heat the gas to temperatures exceeding 100 million degrees, hot enough to strip electrons from any atom. The resulting plasma glows brilliantly in X-rays, creating some of the most luminous objects in the universe. The Bullet cluster, located 3.7 billion light-years away, provides one of the most striking examples. Astronomers observed 2 galaxy clusters that had passed through each other at incredible speeds. The hot gas from each cluster collided and slowed down, forming two distinct clouds. But gravitational lensing measurements revealed that most of the mass, the dark matter, had passed straight through. This observation provided some of the strongest evidence for dark matter's existence. The separation between where the gas ended up and where most of the mass actually resides can only be explained if most of the matter is invisible and non-interacting. These cosmic crashes can trigger the formation of radio halos spanning millions of light years. Magnetic fields stretched and amplified by the collision accelerate electrons to near light speed, causing them to emit radio waves as they spiral around field lines. The result is a ghostly radio glow larger than entire galaxies. The most violent cluster collisions can create bow shocks that propagate outward at thousands of kilometers per second. These cosmic sonic booms compress and heat the surrounding medium, creating structures visible across vast distances. The energy contained in these shocks exceeds the total energy output of billions of supernovae. During the collision, individual galaxies within the clusters experience their own violent encounters. Tidal forces can strip stars from galaxy outskirts, creating long streams of stellar debris that trace the cluster's gravitational dance. Some galaxies may be completely disrupted, their stars scattered into the growing cluster's halo. The collision can trigger massive bursts of star formation as gas clouds within galaxies are compressed by the encounter. These starbursts can increase a galaxy's star formation rate by factors of hundreds, creating brilliant blue regions filled with newly born massive stars that will live fast and die young. But here's what makes galaxy cluster collisions particularly significant. They represent the largest scale on which individual events can be observed in the universe. Beyond clusters, structure exists only in the form of superclusters and cosmic filaments, arrangements so large they're essentially statistical features of the universe rather than distinct objects. Galaxy cluster collisions mark the boundary between individual cosmic events and the large-scale structure of the universe itself. They're the bridge between the world of discrete objects and the realm of cosmology. Yet even these titanic collisions are dwarfed by something that operates on truly universal scales, something that happened once, everywhere, all at the same time, and shaped everything that followed: the Big Bang. 13.8 billion years ago, everything that exists today was compressed into a point smaller than a proton. All the matter and energy in the observable universe, from the smallest quantum particles to the largest galaxy clusters, occupied a space with no dimensions at all. This was the Big Bang singularity, and it represents the ultimate expression of cosmic power, the moment when existence itself began. At this primordial moment, the laws of physics as we understand them break down completely. Temperature and density become infinite. Space and time have no meaning. The four fundamental forces that govern everything in the modern universe were unified into a single, unimaginably powerful interaction. In the first fraction of a second, smaller than the time it takes light to cross a proton, the universe expanded faster than light itself. This period of cosmic inflation stretched space by factors of at least 10 to the 26th power in just 10 to the negative 35th seconds. To put this in perspective, imagine a single atom suddenly growing larger than the observable universe in less time than it takes light to travel across that atom. The expansion was so rapid it defies human comprehension. Space didn't explode into pre-existing emptiness. Rather, space itself was created as the universe grew, carrying matter and energy along for the ride. This is why we say the Big Bang happened everywhere, because everywhere that exists was once the same point. The temperature during these first moments was so high that even the fundamental forces of nature couldn't maintain their separate identities. Gravity, electromagnetism, and the strong and weak nuclear forces were indistinguishable aspects of a single superforce that has never existed since those first instants of creation. As the universe expanded and cooled, this cosmic unity shattered. The forces separated in a series of phase transitions that released enormous amounts of energy. First gravity separated, then the strong force, and finally electromagnetism split from the weak force. Each separation fundamentally changed the nature of reality. During the first 3 minutes after the Big Bang, the universe cooled enough for the first atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons, newly formed from cooling quarks, fused together in a cosmic forge that created most of the hydrogen and helium we see today. The energy density was so extreme that matter and antimatter annihilated each other in constant flashes of pure energy. For reasons still not fully understood, there was slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. This tiny asymmetry is why anything exists today. For 380,000 years after the initial explosion, the universe remained opaque to light. Free electrons scattered photons so efficiently that light could travel only tiny distances before being absorbed and re-emitted. The cosmos was like a glowing fog filled with energy but impossible to see through. Then came cosmic dawn. Electrons and atomic nuclei finally combined to form the first neutral atoms, allowing light to travel freely for the first time. This cosmic clearing created the afterglow we still see today as the cosmic microwave background radiation, a faint echo of creation itself that fills every corner of the sky. The Big Bang was not an explosion in space, but an explosion of space itself. It created time as well as matter, establishing the laws of physics that govern everything from quantum fluctuations to galaxy formation. No event before or since has matched its power to create everything from nothing. But here's the profound realization. The Big Bang didn't just release energy, it created the fundamental structure of reality. It determined that space would have 3 dimensions. It set the strengths of the fundamental forces. It established the properties of elementary particles. Every other powerful phenomenon we've explored, gamma-ray bursts, black holes, supernovae, colliding galaxy clusters, all of them operate within the framework established by the Big Bang. They're powerful, but they're playing by rules they didn't create. The Big Bang made the rules, yet even this cosmic genesis may not represent the ultimate limit of power in our universe. Cosmic inflation. Before the universe was even 1 second old, space itself underwent the most violent expansion in cosmic history. In a period shorter than the time it takes light to cross a proton, the universe grew from smaller than an atom to larger than a grapefruit. This process, called cosmic inflation, represents the most powerful force ever unleashed, stretching space faster than the speed of light and setting the stage for everything that followed. During inflation, space expanded by a factor of at least 10 to the 26th power in just 10 to the negative 35th seconds. The expansion was so extreme that regions of space initially in contact were stretched far beyond any possibility of future communication. The driving force behind inflation was a quantum field called the inflaton, which filled all of space with enormous energy density. Unlike normal matter, this field had a bizarre property. It created more energy as space expanded. The more the universe grew, the more energy became available to drive further expansion. Think of it as cosmic fuel that never runs out. The bigger the fire grows, the more fuel appears to feed it. This is why inflation could proceed so rapidly and for so long before finally ending. Inflation solved several fundamental problems that had puzzled cosmologists for decades. Before inflation theory, scientists couldn't explain why the universe looks nearly identical in all directions. Different regions of the cosmos appear to have the same temperature and density, yet they're so far apart they could never have exchanged energy or information. Inflation explains this by revealing that all these distant regions were once close together, close enough to reach thermal equilibrium, before inflation stretched them to cosmic scales. They look the same because they started from the same initial conditions. Another mystery inflation solved: where are all the exotic relics predicted by particle physics? Grand unified theories suggest the early universe should have produced magnetic monopoles, cosmic strings, and other strange objects. Yet we don't observe them anywhere. Inflation provides the answer. These objects did form, but the rapid expansion stretched them to sizes larger than the observable universe, effectively hiding them beyond our cosmic horizon. They exist, but they're too far away to ever detect. But inflation did more than solve problems. It made predictions. The theory predicted that quantum fluctuations in the inflaton field would be stretched to cosmic scales, creating tiny density variations in the early universe. These ripples would later grow under gravity's influence to become galaxies and galaxy clusters. In the 1990s, satellites measured the cosmic microwave background radiation and found exactly the pattern of fluctuations inflation predicted. The match was so precise it elevated inflation from an interesting idea to the leading theory of the universe's earliest moments. The amount of energy involved in cosmic inflation was staggering. In just a fraction of a second, the inflaton field released more energy than has been produced by every star in the observable universe over the past 13.8 billion years. This energy went into creating new space and filling it with the matter and radiation we see today. When inflation finally ended, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the 28th degrees. This was hot enough to create and destroy particles at rates that would make the cores of the most massive stars seem frigidly cold by comparison. Some theories suggest that inflation didn't occur just once, but is an eternal process continuing beyond our observable universe. In this scenario, our entire cosmos might be just one bubble in an infinite multiverse, where new universes are constantly being born through inflation. If true, this means inflation isn't just the most powerful event in our universe's history. It's an ongoing cosmic process generating infinite universes, each with potentially different physical laws. But whether inflation occurs once or eternally, it represents something unique among all the powerful phenomena we've explored. It didn't just release energy or reshape existing matter, it created space itself, expanding the very arena in which all other events occur. Every other force operates within space. Inflation created space, hypernovae A. Beyond the realm of ordinary supernovae lies something far more violent. When a star containing 50 times the mass of our Sun finally runs out of nuclear fuel, it doesn't simply collapse and explode. Instead, it creates a hypernova. An explosion so energetic it dwarfs regular supernova by factors of 10 to 100. These stellar monsters are rare even on cosmic timescales. Only the most massive stars in the universe can trigger hypernovae, and they must be spinning rapidly when they die. The combination of extreme mass and rotation creates conditions so violent that normal stellar death cannot contain the fury about to be unleashed. When the core of such a star collapses, it forms a black hole almost instantly. But the star's rapid rotation prevents a simple symmetric collapse. Instead, the infalling material creates an accretion disk around the newborn black hole, spinning so fast it becomes a cosmic dynamo generating magnetic fields of unimaginable strength. These twisted magnetic field lines act like springs wound to the breaking point. When they finally snap and reconnect, they launch jets of matter and energy outward at 99.9% the speed of light. These jets bore through the collapsing star like cosmic drill bits, carrying enough energy to power our Sun for billions of years. The jets punch through the star's outer layers and burst into space, creating the gamma-ray bursts we detect from billions of light years away. But the violence doesn't end there. The shock wave from the jet's passage heats the star's interior to temperatures exceeding those in the cores of normal stars, triggering explosive nuclear burning throughout the stellar remnant. Layer after layer of the star explodes outward in a cascade of thermonuclear violence. Carbon burns to neon, neon burns to silicon, and silicon burns to iron in a matter of seconds. The energy released by these rapid fusion reactions adds to the destruction, creating an explosion visible from the edge of the observable universe. A single hypernova can synthesize more heavy elements than dozens of normal supernovae. The extreme conditions create radioactive isotopes that decay over weeks and months, powering an afterglow that continues long after the initial explosion. These cosmic forges produce many of the elements essential for life, scattering them across vast regions of space. The most powerful hypernovae can disrupt star formation across entire regions of galaxies. Their shockwaves compress nearby gas clouds, triggering new waves of stellar birth while simultaneously heating the surrounding medium to temperatures that prevent further star formation for millions of years. In 1998, astronomers detected a hypernova in a galaxy 1.2 billion light-years away. The explosion, designated SN 1998BW, was one of the first hypernovae ever observed in detail. It was associated with a gamma-ray burst, confirming the connection between these ultra-energetic stellar deaths and the most powerful explosions in the universe. Hypernovae may have played a crucial role in the early universe. The first generation of stars, composed only of hydrogen and helium, were likely much more massive than modern stars. When these primordial giants died as hypernovae, they seeded space with the first heavy elements, making possible the formation of planets and eventually life. But hypernovae, despite releasing 100 times more energy than ordinary supernovae, still pale in comparison to events that operate on truly cosmic scales. They're stellar explosions, violent and spectacular, but ultimately local events that reshape only small regions of galaxies. To find power that operates on larger scales, we need to look at phenomena that can reshape entire galaxies or even influence the structure of the universe itself. Cosmic rays. Somewhere in the depths of space, protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles race through the galaxy at 99.9999% the speed of light, carrying individual energies equivalent to a baseball thrown at 60 miles per hour, all compressed into a single atomic nucleus. The cosmic accelerators that create these particles operate on scales and with efficiencies that make our most advanced technology seem primitive. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the 20th electron volts, more than 10 million times the energy achievable in the Large Hadron Collider. A single one of these particles contains enough energy to light a small bulb for a brief moment, all concentrated in an object smaller than a proton. When such particles strike Earth's atmosphere, they create cascades of secondary particles that can trigger detectors spread across thousands of square miles. The primary cosmic ray smashes into an air molecule, creating dozens of secondary particles. These secondaries collide with more molecules, creating more particles, and so on. By the time the cascade reaches ground level, a single cosmic ray has generated millions of particles. The cosmic accelerators responsible for these extreme particles remain one of astrophysics' greatest mysteries. Supernova shockwaves can accelerate particles to high energies, but they cannot explain the most extreme cosmic rays. The electric fields required would need to extend across distances of millions of light years and maintain voltages exceeding 10 to the 20th volts. Active galactic nuclei powered by supermassive black holes represent the most likely cosmic accelerators. The magnetic fields near these objects can store enormous amounts of energy, releasing it in sudden bursts that accelerate particles to relativistic speeds. The jets launched by these black holes create natural particle accelerators millions of light years long. When cosmic ray particles travel through magnetic fields in space, they are deflected and scattered, making it nearly impossible to trace them back to their sources. Only the most energetic particles, those with energies exceeding 10 to the 19th electron volts, travel in nearly straight lines through galactic magnetic fields. These ultra-high energy particles provide our only direct probes of the most extreme acceleration processes in the universe. In 2017, the Pierre Auger Observatory detected cosmic rays arriving from the direction of nearby galaxies with active galactic nuclei, providing the first hints about where these particles might originate. The interaction of cosmic rays with magnetic fields creates some of the most spectacular phenomena in astrophysics. When these particles spiral around field lines, they emit synchrotron radiation that glows across the electromagnetic spectrum. The radio emission from our galaxy is largely produced by cosmic ray electrons spiraling through the Milky Way's magnetic field. Cosmic ray acceleration can occur through multiple mechanisms. Shockwave acceleration happens when particles repeatedly cross shock fronts, gaining energy with each crossing. Magnetic reconnection can accelerate particles impulsively when twisted field lines suddenly snap and reconfigure themselves. The most extreme cosmic ray events might involve mechanisms we haven't yet discovered. Some theories suggest that the decay of exotic particles left over from the Big Bang could produce cosmic rays with energies exceeding anything possible through conventional acceleration. Cosmic ray interactions with gas and dust in space create secondary particles including gamma rays, neutrinos, and positrons. These secondary products carry information about both the cosmic rays themselves and the environment through which they travel. But here's what makes cosmic rays particularly significant in our search for ultimate power. They represent energy in its purest, most concentrated form, individual particles carrying macroscopic amounts of kinetic energy. They're the universe's way of focusing the output of galaxy-scale phenomena into subatomic bullets. Yet even these incredibly energetic particles are just messengers carrying news of even more powerful processes occurring at their sources. Quantum vacuum energy. In the apparently empty space between atoms, between planets, between stars, the quantum vacuum seethes with invisible activity. Virtual particles pop into existence and annihilate each other in time so brief they exist below the threshold of direct observation. Yet these quantum fluctuations contain enough theoretical energy to reshape reality itself. The quantum vacuum is not truly empty, but filled with zero-point energy that exists even at absolute zero temperature. Every cubic centimeter of space contains virtual photons, electron-positron pairs, and countless other particle combinations that borrow energy from the vacuum and must pay it back before quantum mechanics notices the violation. This constant creation and destruction of virtual particles creates an energy density that physicists have attempted to calculate. The results are startling. According to quantum field theory, the energy density of the vacuum should be enormous, perhaps 10 to the 120th times larger than what we observe as dark energy. This enormous discrepancy, known as the cosmological constant problem, represents one of the greatest failures of theoretical physics. If these calculations were correct, space itself would be so energetically unstable that atoms couldn't exist. The universe would tear itself apart instantly. Yet quantum vacuum fluctuations do produce measurable effects that confirm their reality. The Casimir effect demonstrates that two metal plates placed very close together will be pushed toward each other by the pressure of virtual particles. The space between the plates excludes certain wavelengths of virtual photons, creating an imbalance that generates a tiny but detectable force. In 1997, physicist Steve Lamoureux measured the Casimir force between two gold-coated plates and found results matching quantum predictions to within 5%. The vacuum between the plates really does exert measurable pressure. Virtual particles near the event horizons of black holes can become real through a process discovered by Stephen Hawking. One member of a virtual particle pair can fall into the black hole while the other escapes, causing the black hole to slowly evaporate. This Hawking radiation represents the conversion of vacuum energy into real particles. A small black hole with the mass of a mountain would evaporate completely in about 10 to the 19th years, releasing its energy gradually through Hawking radiation. But in its final moments, as it shrinks to subatomic sizes, the evaporation rate accelerates exponentially. In its last second of existence, it would explode with the energy of millions of nuclear weapons. In the early universe, quantum vacuum fluctuations were stretched to cosmic scales during inflation. These microscopic energy variations became the seeds of all large-scale structure, growing under gravity's influence to form galaxies and galaxy clusters. Every star, planet, and living being owes its existence to quantum fluctuations that occurred when the universe was smaller than an atom. Some theories suggest that our entire universe originated from a quantum vacuum fluctuation, a brief deviation from nothingness that somehow became permanent. In this scenario, the Big Bang itself was not the beginning of time, but rather the moment when a virtual universe became real. If vacuum energy could be harnessed, it would provide an effectively unlimited source of power. A device the size of a coffee cup could theoretically extract enough energy to power human civilization for billions of years, making all other energy sources obsolete overnight. But extracting vacuum energy faces enormous theoretical and practical obstacles. The vacuum is already in its lowest energy state, at least locally. To extract energy, you would need to somehow create regions of even lower vacuum energy, which may not be physically possible without exotic physics. The vacuum energy puzzle connects directly to our search for ultimate power. If quantum fluctuations really do contain the energy densities suggested by theory, then the most powerful thing in the universe isn't some distant astrophysical object. It's the empty space right in front of you. But this raises a profound question. Is potential energy the same as actual power? The vacuum may contain enormous theoretical energy, but if we can't access it, does it count? Primordial black holes. In the first moments after the Big Bang, when the universe was smaller than an atom and Denser than the core of a neutron star, tiny fluctuations in density could have collapsed to form black holes more massive than mountains yet smaller than atoms. These primordial black holes would possess gravitational fields so intense they warp space and time on scales invisible to the human eye. Unlike black holes formed from collapsing stars, primordial black holes could have any mass. Some might weigh as little as a paperclip, while others could exceed the mass of our sun. The smallest ones would be quantum objects, where the strange rules of quantum mechanics clash with the absolute authority of general relativity in ways we barely understand. A primordial black hole with the mass of a mountain would be smaller than a proton, yet possess a gravitational field millions of times stronger than anything we can create on Earth. Space and time around such objects would be twisted into extreme geometries, creating regions where familiar concepts of distance and duration break down. These microscopic monsters would be among the most violent objects in the universe. According to Stephen Hawking's calculations, black holes emit radiation and slowly evaporate over time. The smaller the black hole, the faster it evaporates, and the more violently it dies. A primordial black hole with the mass of a large asteroid would explode with the energy of millions of hydrogen bombs. The final moments of a small primordial black hole's life would be spectacular. As it shrinks to subatomic sizes, the rate of evaporation accelerates exponentially. In its last second of existence, it would release more energy than our sun produces in an entire year, all concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in large numbers, they could solve one of cosmology's greatest mysteries, the nature of dark matter. These invisible objects would exert gravitational influence without emitting light, exactly matching the properties astronomers observe throughout the universe. The search for primordial black holes has led scientists to examine extreme environments. When these objects pass through stars, they would heat the stellar material and cause detectable changes in brightness. When they collide with neutron stars, they might trigger observable gravitational wave signals. Some primordial black holes might have grown over cosmic time by accreting matter and merging with other black holes. These objects could now be lurking in the dark spaces between stars, invisible predators waiting to encounter matter they can devour. Their gravitational lensing effects might occasionally bend and magnify light from distant stars, the most massive primordial black holes could have served as seeds for the supermassive black holes we observe at the centers of galaxies today. This would solve the puzzle of how such enormous black holes formed so early in the universe's history when normal stellar evolution had barely begun. In 2016, when LIGO detected gravitational waves from merging black holes, some scientists wondered if these might be primordial black holes rather than stellar remnants. The masses were in a range that's difficult to explain through normal star formation, but consistent with primordial black hole predictions. But here's what makes primordial black holes particularly intriguing in our search for ultimate power. If they exist, they would be direct relics of the Big Bang, objects that formed in the universe's first fraction of a second and survived unchanged for 13.8 billion years. They would be time capsules carrying information about conditions in the primordial cosmos. Yet even these exotic objects, if they exist, are just consequences of more fundamental processes. They're products of quantum fluctuations in the early universe, effects rather than causes. Magnetorotational supernova A. In the heart of a dying star spinning at 1,000 revolutions per second, magnetic fields a trillion times stronger than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova, where the combination of extreme rotation and magnetic power creates explosions that dwarf even the mightiest gamma-ray bursts. When the most massive stars in the universe reach the end of their lives, some possess magnetic fields comparable to those found on magnetars. If such a star is also rotating rapidly when its core collapses, conservation of angular momentum spins the collapsing core even faster, like a figure skater pulling in their arms. As the stellar core shrinks from the size of Earth to just 12 miles across, its rotation rate increases by millions of times. The magnetic field lines frozen into the collapsing plasma become twisted and amplified until they reach strengths approaching the theoretical limits allowed by physics. These fields become so powerful they can influence the structure of space-time itself. The magnetic pressure exceeds the pressure inside atomic nuclei. Field lines stretched to the breaking point store enough energy to power our sun for billions of years. When these magnetic structures finally become unstable and reconnect, they release stored energy in violent magnetic explosions that make solar flares seem like gentle breezes. Charged particles caught in these fields are accelerated to energies far exceeding anything achievable in our most advanced particle accelerators. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo more powerful than anything else in the universe. These magnetorotational explosions can launch jets of magnetized plasma at velocities approaching the speed of light, creating beams of destruction that could sterilize planets from millions of light years away. Unlike the jets from ordinary gamma-ray bursts, these magnetically driven outflows maintain their focus across intergalactic distances. The magnetic fields act like invisible guide rails, keeping the jets columnated even as they travel through turbulent intergalactic gas. The magnetic fields generated during these explosions are so strong they affect the vacuum of space itself. At field strengths exceeding 10 to the 15th Gauss, quantum vacuum becomes birefringent, splitting light into separate polarizations and creating optical effects that exist nowhere else in nature. Matter exposed to these extreme magnetic fields experiences effects that seem impossible. Atoms become elongated into needle-like shapes aligned with the field. The chemical bonds that hold molecules together are twisted and distorted beyond recognition. Even fundamental particles begin to behave in strange new ways. The energy released by a magnetorotational supernova can exceed that of a normal supernova by factors of hundreds. The explosion synthesizes exotic isotopes that cannot be created under any other conditions, forging elements that exist for mere seconds before decaying into more stable forms. These cosmic alchemical laboratories create materials that push the boundaries of nuclear physics. They produce neutron-rich isotopes far from the valley of stability, providing insights into how matter behaves under the most extreme conditions imaginable. But magnetorotational supernovae are incredibly rare. The conditions required, extreme mass, rapid rotation, and powerful magnetic fields, all occurring in the same star, happen perhaps once per million ordinary supernovae. We may observe only a handful in the entire observable universe each year. This rarity raises an important question about power. Is something more powerful if it occurs frequently, or if it's exceptionally rare but extraordinarily intense? Does rarity diminish power or enhance it? Vacuum decay. Hidden in the quantum foam that underlies all reality lurks a possibility so terrifying it could end everything we know in an instant. The Higgs field, which gives all particles their mass, might not be in its lowest possible energy state. If this field suddenly dropped to its true minimum, it would create a bubble of destruction that expands at light speed, rewriting the laws of physics and annihilating everything in its path. The Higgs field permeates every corner of space, existing even in the vacuum between atoms. Like a ball balanced on a hill, this field might currently sit in what physicists call a false vacuum state. It appears stable, but it could potentially roll down to an even lower energy level, fundamentally changing the nature of reality itself. If vacuum decay began anywhere in the universe, it would create an expanding sphere of true vacuum moving outward at exactly the speed of light. Nothing could escape this cosmic wave of destruction because no information or matter can travel faster than light. We would have no warning of its approach until the moment it arrived. Inside the bubble of true vacuum, the fundamental constants of nature would be different. Particles might have different masses or might not exist at all. Atoms as we know them could not form. The strong nuclear force might be weaker, causing all atomic nuclei to fall apart instantly. Chemistry and biology would become impossible. The energy difference between false vacuum and true vacuum would be released as the bubble expanded. This energy could exceed the rest mass energy of all matter in the universe, making vacuum decay more energetic than converting every proton, neutron, and electron into pure energy. The universe would be flooded with more power than every star and galaxy combined. Current calculations based on measurements from the Large Hadron Collider suggest that our vacuum might indeed be metastable, balanced precariously on the edge of stability. The Higgs boson mass measured in 2012 falls in a range that makes the vacuum stable enough to last billions of years, but not completely stable forever. High-energy events like cosmic ray impacts or quantum fluctuations might potentially trigger the transition. Even the evaporation of black holes through Hawking radiation could, in theory, nucleate a bubble of true vacuum in the intense fields near the event horizon. The terrifying aspect of vacuum decay is its inevitability if the false vacuum state exists. Quantum mechanics guarantees that any metastable state will eventually decay, even if the probability is incredibly small. Over the vast timescales of cosmic evolution, even the most unlikely events become certain. But here's the counterintuitive aspect. Vacuum decay would be the ultimate reset button, but also the ultimate act of creation. Everything that has ever existed would be erased and replaced by a universe with fundamentally different physics. The new vacuum state might allow for entirely different forms of matter, different forces, perhaps even different forms of complexity we cannot imagine. Some theories suggest that vacuum decay might have occurred multiple times in our universe's history, with each transition creating new regions. With different physical laws, we might be living in just one bubble among many, surrounded by realms where the rules of existence are utterly alien. If vacuum decay represents the ultimate destructive power, the ability to literally rewrite the laws of physics, then it might also represent the ultimate creative power, the ability to generate entirely new realities with new possibilities. This brings us to a profound realization. Perhaps we've been asking the wrong question all along. The multiverse. Beyond the edge of our observable universe, beyond the most distant galaxies we can ever hope to see, lies something that dwarfs all the cosmic forces we have encountered. If the multiverse exists, our entire universe, with all its supernovae, black holes, and gamma-ray bursts, becomes nothing more than a single bubble in an infinite ocean of realities. In the eternal inflation scenario, our Big Bang was not a unique event, but one of countless explosions occurring continuously throughout higher dimensional space. New universes are constantly being born as quantum fluctuations trigger inflation in regions of false vacuum, creating an ever-expanding tree of cosmic domains. Each universe within this multiverse could have completely different fundamental constants. In some, gravity might be stronger or weaker, changing how stars form and evolve. In others, the electromagnetic force might have different strength, making atoms impossible or creating matter with properties we cannot imagine. The strong nuclear force could be altered, preventing nuclear fusion or allowing elements that cannot exist in our reality. The ratio of matter to antimatter might be different. The number of spatial dimensions could vary. Every possible configuration of physical laws might exist somewhere. The total energy contained within an infinite multiverse would literally be infinite, making it the ultimate expression of cosmic power. Every possible configuration of matter and energy, every conceivable physical law, every potential history would exist somewhere within this vast ensemble of realities. Some regions of the multiverse might contain universes that expand forever, while others collapse back on themselves in big crunches that mirror their Big Bang origins. Still others might oscillate between expansion and contraction, creating cyclic cosmologies that repeat endlessly. In certain interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event occurs with multiple possible results, the universe splits into separate branches, each containing a different outcome. This quantum multiverse would be constantly growing, branching with every quantum interaction throughout all of existence. The number of parallel universes would increase exponentially with each passing moment, creating an incomprehensibly vast landscape of reality. The anthropic principle suggests that we observe our universe's particular combination of physical constants because only this combination allows observers like us to exist. In a multiverse containing all possible combinations of physical laws, conscious beings would necessarily find themselves in universes capable of supporting consciousness, no matter how unlikely such universes might be. This means our universe might not be typical or special. It might simply be one of the rare bubbles where the conditions allow for complexity, structure, and ultimately awareness. Most universes in the multiverse might be sterile, empty, or hostile to any form of organization. If the multiverse exists, it would represent power on a scale that makes even the Big Bang seem small. The Big Bang created our universe, but eternal inflation creates infinite universes. The Big Bang established one set of physical laws, but the multiverse explores all possible sets of laws. But here's the crucial question. If the multiverse exists beyond our ability to observe or interact with it, does it count as powerful in any meaningful sense? Power implies the ability to influence or affect something. If other universes are forever beyond our reach, isolated by the cosmic horizon, do they have power over our reality? This question forces us to confront the deepest meaning of power itself: consciousness and observation. We've journeyed through the cosmos, examining forces of unimaginable magnitude. We've witnessed gamma-ray bursts that outshine trillion stars, black holes that tear holes in space-time, and inflation that created space itself. But there's one power we haven't yet considered, the power that makes any of this matter at all: consciousness, the ability to observe, to understand, to give meaning to the universe. In quantum mechanics, observation plays a fundamental role in determining reality. Before a quantum system is measured, it exists in a superposition of all possible states. The act of observation collapses these possibilities into a single, definite outcome. Without observers, quantum mechanics suggests reality itself might be fundamentally uncertain. This doesn't mean consciousness literally creates reality. That's a misinterpretation. But it does mean that conscious observation transforms potential into actuality, indefinite into definite. In a universe without observers, quantum superpositions might persist indefinitely, never resolving into the concrete reality we experience. Consider the early universe before any conscious beings existed. Quantum fluctuations during inflation created density variations that later became galaxies. But did these fluctuations have definite values before anything could observe them? Or did they exist in quantum superposition until the first observers emerged billions of years later? Some interpretations of quantum mechanics suggest that observation retroactively determines past states. When we measure the cosmic microwave background radiation today, we might be collapsing quantum superpositions that have persisted since the Big Bang, finally giving them definite values 13.8 billion years after they formed. But consciousness does more than collapse quantum wave functions. It transforms meaningless physical processes into comprehensible narratives. The universe contains no inherent meaning. Meaning is something consciousness creates. A supernova is just matter rearranging itself according to physical laws. But to a conscious observer, it becomes a spectacular cosmic event, a source of heavy elements essential for life, a warning about stellar evolution, a reminder of our cosmic origins. Consciousness transforms physics into story. The universe spent 13.8 billion years creating the conditions necessary for consciousness to emerge. From quantum fluctuations to atoms, from atoms to molecules, from molecules to stars, from stars to planets, from planets to life, from life to awareness. Every force we've explored played a role in this progression. The strong nuclear force holds atoms together. Electromagnetism allows chemistry. Gravity assembles planets and stars. Supernovae scatter heavy elements. All of these processes had to occur in precise sequence for consciousness to arise. In this sense, consciousness might be the ultimate expression of cosmic power, not because it's energetically powerful, but because it's the universe's way of knowing itself. Through conscious beings, the cosmos examines its own structure, discovers its own laws, and contemplates its own fate. You are made of stellar ashes and quantum fluctuations. The calcium in your bones was forged in supernova explosions. The iron in your blood was scattered by dying stars. The gold in any jewelry you wear came from neutron star collisions. You are literally assembled from cosmic debris, but you're more than just rearranged stardust. You're stardust that has organized itself in such a way that it can think, feel, and understand. You're the universe looking back at itself, comprehending the forces that created you. This transforms our search for the most powerful thing in the universe. We've been looking outward, examining ever larger and more energetic phenomena. But perhaps true power isn't about energy or scale. Perhaps it's about transformation, understanding, and the ability to give meaning to existence itself. The answer: we set out to find the most powerful thing in the universe. We examined forces that operate on every scale of existence, from the strong nuclear force binding quarks in distances smaller than a proton to dark energy stretching space across billions of light years. We witnessed gamma-ray bursts that outshine trillion stars in seconds. We explored black holes that bend space-time into impossible geometries. We saw neutron star collisions that forge gold and platinum. We contemplated the Big Bang that created everything from nothing, and inflation that expanded space faster than light itself. Each phenomenon we explored possessed extraordinary power in its own domain, but each also had limitations. The strong nuclear force is incredibly powerful, but operates only at subatomic distances. Gamma-ray bursts are spectacularly energetic but brief. Black holes trap everything, yet they're constrained by the Eddington limit. Even the Big Bang, which created our universe, established only one set of physical laws. So what is the most powerful thing in the universe? The answer depends on how you define power. If power means raw energy output, the answer is the Big Bang or cosmic inflation, events that released more energy than all subsequent cosmic processes combined. If power means energy density, the answer might be the strong nuclear force or the quantum vacuum, where unimaginable energy lurks in microscopic volumes. If power means gravitational influence, the answer is black holes, objects so dense they tear holes in space-time and trap light itself. If power means reach across space, the answer is dark energy, the only force capable of overpowering gravity on cosmic scales and determining the universe's ultimate fate. If power means longevity, the answer is fundamental forces that have operated unchanged since the first moments of creation. But perhaps true power isn't about energy or force at all. Perhaps it's about transformation and creativity. The universe is not just powerful, it is creative. It transforms hydrogen into helium through fusion. It converts dying stars into neutron stars and black holes. It forges heavy elements in supernova explosions. It assembles planets from stellar debris. It organizes matter into living systems. And ultimately, it creates consciousness, the ability to understand all of this. Every force we've explored represents the universe's creativity expressing itself in different ways. The strong force creates atomic nuclei. Gravity creates stars and galaxies. Supernovae create heavy elements. Neutron star collisions create gold. Each process is the universe discovering new ways to organize matter and energy. The most remarkable thing about the universe is not its capacity to destroy, but its capacity to create complexity from simplicity, to build atoms from quarks, molecules from atoms, stars from molecules, planets from stars, life from planets, and consciousness from life. This progression required 13.8 billion years and every force we've discussed. The strong force had to be precisely strong enough to bind nuclei, but not so strong that all hydrogen fused immediately. Gravity had to be weak enough for structures to form, but strong enough to hold them together. The electromagnetic force had to allow chemistry, but not overwhelm nuclear binding. If any fundamental constant were slightly different, this progression might not have occurred. The universe might have remained forever simple, just hydrogen expanding through empty space, or collapsing immediately into a black hole, or flying apart so fast that no structures could ever form. But instead, the universe found a path from simplicity to complexity, from uniformity to diversity, from unconsciousness to awareness. So here's the final answer. The most powerful thing in the universe is the universe itself, not as a collection of separate forces, but as a unified system capable of creating, transforming, and ultimately understanding itself. You are proof of that power. You exist because the strong force binds atoms, because gravity assembled planets, because supernovae scattered heavy elements, because stars provided energy, because chemistry allowed life, because evolution created complexity. Every force we've explored had to work in precise harmony for you to exist. And now you can comprehend the very forces that created you. The universe has become aware of itself through you. That is power beyond anything we've witnessed. The power not just to exist, but to know, to understand, and to wonder at existence itself. The universe's most powerful achievement may ultimately be its capacity to ask the question, what is the most powerful thing in the universe? And to realize that the answer includes the questioner.